Good morning, everyone. I'm Pranali, your host for today. I welcome each and everyone for today's Sadgunsang Meet. This is our 282nd virtual webinar. Topic for today is metals and metallurgy for oil and gas industry to control and mitigate corrosion, which shall be taken by Dr. G.S. Thanki. Agenda for the Sadgun Summit, particulars, virtual inauguration by Dr. Sundar Kataria, invoking the blessing of deity, chanting of Gayatri Mantra, introduction of speaker, presentation by Dr. G.S. Thanki sir, question and answer session, closing session. Dr. Sundar Kataria, Chairman and Managing Director of ICS Group Companies, Sadgunsang conceived and led by Dr. Sundar Kataria, driven with a mission to elevate the quality, safety, and environmental awareness levels of industry. Sadgunsang is a series of educative, informative events aiming to illuminate professionals on possible solutions to current issues of industry and economy. Designation and organization. Chairman and Managing Director of International Certification Services Private Limited, Academic Qualification, Mechanical Engineer AIM, Honorary Doctorate, Business Management, Experience, Nuclear RAP. He started his career in building India's first nuclear power plant at Rawatbhatta, Kota, Rajasthan. Oil and Gas EIL. He contributed in developing India's first oil and gas field at Bombay High since its inception. DNV. He was a head of industry and offshore development with DNV for 2 decades. ICS. He is a founder of a first Indian conformity assessment and inspection body known as International Certification Services Private Limited, which is a provider of a total quality solution under single umbrella with a wide spectrum of services. Achievements and awards. Lifetime Achievement Award of NACE Corcon. Received several national and international awards. Now I request Dr. Sundar Kataria sir to virtually inaugurate today's session.
शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः शत्रुबुद्धिविनाशाय दीपज्योतिर्नमोऽस्तुते दीपज्योतिर्नमोऽस्तुते शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः.
Please join us for the recitation of the Gayatri Mantra.
Om Bhurbhuvah Swaha.
Om Bhurbhuvah Swaha. Tatsaviturvarenyam Bhargo Devasya Dhimahi Dhiyo Yona Prachodayat. Om Bhurbhuvah Swaha. Tatsaviturvarenyam Bhargo Devasya Dhimahi Dhiyo
Introduction of the keynote speaker. Dr. G.S. Thanki, Designation and Organization, Director and Principal Consultant, Corrosion Control and Monitoring Consultancy, Principal Corrosion Management Consultant at Corrosafe Consultants Private Limited, Gujarat. Academic qualification, recognized PhD guide at MS University of Baroda, associated with postgraduate and doctoral academic programs in metallurgy and corrosion. Initiated the postgraduate diploma course in corrosion technology at MS University of Baroda. Served as member, board of studies, and examiner and paper setter for the graduate and postgraduate in metallurgy. Achievements and awards, recipient of gold plate from the Indian Institute of Metals. Awarded gold medal for India by ABI INC USA. Honored with Lifetime Achievement Award from NACE. Recipient of Indian Achievers Award for Industrial Development from ITRA by the Vice President of India. Served as corrosion expert in an international arbitration hearing in Paris 2017. Convened and led international conferences on corrosion management, New Delhi and Mumbai 2015 and 2017. Experience over 50 plus years of experience in corrosion engineering and management, 15 plus years in senior advisory roles. Former head GSFC Research Center, member secretary GSFC Science Foundation, international consultant to World Bank, UNESCO and global firms, Germany, Sweden, UK, conducted corrosion auditors across industries, fertilizers, pharma, power, petrochemicals, cement, automotive, etc. Delivered training programs to 80 plus corporate organizations worldwide. Published 65 plus technical papers. Featured on Doordarshan. Extensive global exposure, USA, Europe, Middle East, China, Japan, Thailand. Consultant for KfW Germany, Solar PV Corrosion Project 2020. Advisor to UPL Industries and global organizations associated with global energy talent. Welcome, Dr. G.S. Thanki. Over to you, sir.
Thank you very much. I'm indebted for such a introduction of mine. I'm feeling very humble with you, and I think I will share now this with you. Is it eligible to you?
No, sir.
Something? No.
No.
Okay, I will go back again. I will show it. Is it eligible?
Yes, it's visible, sir.
Thank you. Thank you.
You can on your video also, sir.
Okay. So let us start our something a dialogue under the name of webinar. I'm indebted to my very good friend Dr. Sundar Kataria. He remembered me to share something, whatever I have gathered in my long many years, whatever the wisdom and vision I have developed. Only I give the name as experience means many mistakes might have done in the past. I'm giving good name as experience. Let us start, sir. Let us start with a number. You know this astronomical number, 2, 5, and how many numbers are there? 11. This is $2.5 trillion. It's really a very big number, but that number we are going to touch today in a webinar. According to NAS, that is the global annual cost of corrosion. In the oil and gas sector, corrosion is not just a maintenance headache, it is one of the single greatest threats to our operational viability and environmental stewardship. We have all seen what happens when the wrong grade of alloy hits at a severe environment or when a coating fails permanently, prematurely. This fix it when it breaks model is that. Today, to stay competitive in 2026, we have to be proactive. In this webinar, we are moving beyond the basics. We are looking at high performance alloys, smart monitoring, and the precise metallurgical choices that define the difference between a 30-year asset and a 5-year disaster. Let us get started. You are the guardians of the infrastructure. By the end of the session, you will have a specific new strategy or piece of knowledge to apply to your current projects. Corrosion is not just a technical failure, it is a financial leak. Every millimeter of wall loss we prevent is a direct contribution to the company's bottom line and our ESG commitments. As we push into more shower and ultra deep environments, the margin for error in our material selection has shrunk to near zero. We are no longer just choosing metals. We are engineering survival. We have all seen a stress corrosion crack that looked like a lightning bolt through a pipe. Let us go through a few slides which will make things little easier to again forward with various slides which I am going to share with you. For example, this one. You have seen this stress corrosion crack on a pipe. Very disastrous path. Okay. Next one is showing the corrosion, showing the tension and magnified details. This is a micro crack like this. Microscopic piece becoming stress concentration. You see, the picture tells me a lot. Tensile stress, you can see localized corrosion pits under tensile stress. Leakage starts. In the magnified form, it shows the corrosion pits and micro cracks. Next one will show you something better. Lightning propagation, the but mate. Why it is so it is not so. It's okay. Lightning pattern crack propagation. The branching fissures radiate from the main crack, capturing the dynamic energy of stress corrosion spreading through the pipe. These are step-by-step pictures I'm showing you how dangerous this corrosion can become in our oil and gas industries. Crack propagation, the fishbone pattern. Left-hand side shows the main crack, branching cracks, and spreading like a lightning bolt. This advanced, well, wait, this one has to be good. Croak advances along grain boundaries under corrosive attack. Next one for you, little more. The pipe rupture rendered with jagged, torn edges and a dynamic burst of fluid escaping under pressure. This is a combined stress and corrosion lead to sudden failure. And these arrows clearly mark the intergranular attack zones where corrosion follows grain boundaries. The insect magnified view reveals the crystalline fracture path, making the atomic level damage visually. You can see the crystalline path of corrosion. This particular slide speaks a volume, how it happens. The spectrography reveals the signature of stress corrosion cracking. I'm just touching one only important point is going to happen big way when sulfur is present in the oil. Now here's the last one. It is we are showing a protection through vigilance against corrosion war, which I'm trying to show you. A protection through vigilance war in the corrosion war visual, a powerful composition contrasting defense and decay. The left side shows glows in green blue, symbolizing coating, integrity, inhibitors, and awareness. The right burns in orange red, representing corrosion's relentless assault. At the center, the vigilant shield and watchful light embody corrosion war echoes, alertness as the ultimate protection. This is a message which I want to pass through this my webinar to all your people, those who are interested to learn and to practice in the their own day-to-day life. The sequence now tells us a complete forensic and motivational story, from pit initiation to rupture, culminating in vigilance as the ultimate protection. Those are not just failures, they are signatures of a metallurgical mismatch. Today, we learn how to read these signatures before they write a check we can't cash. In the oil and gas industries, corrosion is not merely a maintenance challenge, it is a critical safety, economic, and environmental concern. Managing it requires a sophisticated understanding of metallurgy, environmental chemistry, and material science. So I try to club all the three together: metallurgy, environmental chemistry, and material science. Single one cannot give you the total foundation to control corrosion. The industry's approach to corrosion mitigation relies on a hierarchy of defenses. Material selection, that is metallurgy, environmental modification through inhibitor, water treatment, and surface protection, coatings and cathodic protection. First, the core corrosion mechanism. Let us understand that. Before selecting materials, engineers must characterize the threat environment. The presence of water is the catalyst for nearly all corrosion in ONG. Sweet corrosion, that means CO2, when CO2, carbon dioxide, dissolves in produced water, it forms carbonic acid that is known as H2CO3, which attacks carbon steel. This often results in localized mesa attacks or pitting. This is the reaction that way it takes place. Sour gas H2S. H2S, that means hydrogen sulfide, is highly toxic and leads to sulfide stress cracking and hydrogen induced cracking. Even trace amount of H2S can cause sudden brittle failure in high strength states. Microbiologic induced corrosion, MIC, is well known as fondly we talk as MIC, sulfate reducing bacteria, thrive in stagnant zones or under deposits, producing hydrogen sulfide locally and accelerating pitting corrosion. Then comes the chloride stress corrosion cracking, highly relevant for stainless steels in hot, saline environments, common in deep sea production. Let us see the metallurgical solution, the hierarchy of resistance. Let us understand one by one. Material selection is a primary line of defense. Engineers choose metals based on their resistance profile versus cost and mechanical requirements of the application. First, let us see carbon and low elasticity. The workhorse of the industry for onshore pipelines and well casing, where the environment is non-corrosive or can be easily treated. How would you mitigate? Economical, but relies entirely on external coatings like fusion bond epoxy, internal liners, or heavy dosing of chemical corrosion inhibitors. Metallurgical limitations, high susceptibility to H2S cracking. Therefore, specific
Sir,
engineers must navigate the resistance profile, a delicate balancing act between chemical stability, mechanical property, that means yield strength and ductility, and project economics. Economics is always hovering on the people, those who are going to have the project to be completed, delivery in time with the right type of construction without cutting corners.
sir, your screen is not visible.
Carbon and low velocities.
Sir, your screen is not visible.
Not visible. What
No.
happened? Meet. How it can happen? Is it visible now?
Yes, yes.
Mhm. Is it visible now?
Yes, it's visible, sir.
Okay, okay. First, let us see
Doc-
carbon and low yellow steels.
Dr. Thanki, can you
Yes,
go
sir.
back 5 minutes before, because there was no audio also available,
Okay,
and
I will
somehow
go.
the slides were also not visible. If we
Okay, I
can
will.
go
Okay, I
back
will go back. If it
to
is 17 number side, I
to
will go to 15 or 14. Okay.
yeah, thank you.
Okay. Is it visible now?
Yes, yes, it's visible.
Okay, it is a back slide only.
Yes.
I will go a little fast in this case.
Okay.
Okay, let us go with this 17 number slide. Is a carbon and low yellow steels. Often referred to as the workhorse for industry, carbon and low yellow steels form the backbone of global infrastructure. While they lack the glamorous stainlessness of high-end alloys, their predictability and cost efficiency make them indispensable. Primary use cases. Onshore pipelines, long-distance transport of hydrocarbons where the fluid is sweet, that means low carbon dioxide and hydrogen sulfide content. Well casings, providing structural integrity for oil and gas wells where the geological environment is stable or manageable via chemical treatment. Structural component, frameworks and supports where atmospheric exposure is the only concern. So now the mitigation strategies, the external defense. Because carbon steel lacks innate corrosion resistance, it relies on a system of protection rather than its own chemistry. External coatings, fusion bonded epoxy acts as a physical barrier. It is a thermoset polymer applied to heated pipes, creating a robust shield against soil-borne moisture and oxygen. In the internal liners, in more aggressive environment, plastic or cement liners prevent the produced fluids from touching the steel. And chemical corrosion emitter, CCIS, we see only. This involves injecting filming chemicals into the flow stream. These chemicals bond to the inner pipe wall, creating a microscopic protective layer. It is a continuous operational expense, OPEX, versus the capital expenses that is known as CAPEX or of metal alloys. It is different between OPEX and CAPEX. Metallurgical limitation and shower service. The greatest weakness of standard carbon steel is its vulnerability to hydrogen sulfide, a phenomenon known as sour service. The chemistry of failure, what is that? When hydrogen sulfide reacts with moisture on a steel surface, it releases atomic hydrogen, and these tiny atoms diffuse into the steel lattice. If the steel is too hard or contains impurities, hydrogen collects at trap sites, creating internal pressure that leads to sulfide stress cracking or hydrogen-induced cracking, like this. You can just understand this one, sulfide stress cracking. Then comes another one. It is a hydrogen-induced cracking. And this one is the manifestation how it looks like on surface when hydrogen-induced cracking is taking place. To combat this, engineers utilize specialized sour surface grades governed by the NAS MR 0175 oblique ISO 15156 standards. Hardness control, generally limited to 22 HRC, that means Rockwell hardness C. Harder steels are more brittle and prone to cracking under hydrogen embrittlement. Cleanliness, reducing sulfur and phosphorus levels during the melting process to eliminate the inclusion sites where hydrogen bubbles can form. Heat treatment, precise quenching and tempering to ensure a uniform microstructure, typically fine-grained tempered martensite or ferrite perlite. I'm going with a comparison, a snapshot of carbon steel versus environment. First is we are showing the feature is initial cost. Standard carbon steel is baseline, say 1x, and sour service premium 1.2x to 1.5x. S2S resistance, low, high risk of brittle failure, whereas high, when sour system are there, higher controlled hardness. You have to control the hardness, otherwise it will crack. The third feature is the primary failure mode. General pitting and uniform thinning in standard carbon steel, whereas next grade, brittle cracking and blistering. Main advantage, high availability and weldability, whereas safety, toxic environment is a next grade. Carbon steel alloys, stainless steel. Moving up the hierarchy, we transition from metals that require help, that means coatings and welders, to materials that possess increasing resistance. Stainless steels are defined by a minimum chromium content of 10.5%, which reacts with oxygen to form a self-healing microscopic passive layer of chromium oxide. Martensite stainless steel, that is the 13 CR family. If carbon steel is the workhorse, 13 chrome is the specialist. It is the go-to choice for sweet wells where CO2 is the primary threat. What is the advantage? High strength to weight ratio and excellent resistance to carbon dioxide corrosion without the need for continuous chemical inhibition. The trade-off, poor weldability. These are typically used for downhole tubulars, that means production tubing, rather than long distance welded pipelines. What are the limitations? Highly sensitive to fluorides and high temperatures. In hot, salty environments, the passive layer breaks down, leading to rapid pitting. Next is the Austin stainless steel, which are very fondly known as 300 series, recognized by the classic 316L grade. These alloys contain nickel and molybdenum to enhance stability and corrosion resistance. What is the advantage? Exceptional ductility and toughness, even at cryogenic temperatures. The addition of 2 to 3% of molybdenum significantly improves resistance to pitting in chloride-rich, that means saltwater environment. But what is the critical weakness? Chloride stress corrosion cracking. In hot, chloride-rich environments, these steels can fail catastrophically and suddenly through fine branching cracks, even if the metal looks shiny and new on surface. Next comes the duplex stainless steel. That is what we call hybrid. Duplex steels are a metallurgical best of both worlds, featuring a microstructure that is roughly 50% ferrite and 50% austenite. Best of both worlds. That's we are going ferrite and austenite. Mechanical superiority, roughly twice the yield strength of standard austenite steels, allowing the thinner walls and lighter structures. That means, from the cost point of view, also it wins the race. Its corrosion profile is what? Exceptional resistance to stress corrosion cracking and pitting. They are the standard for subsea manifolds and flow lines where the internal fluid is aggressive and the external environment is severe. The PRN number. Engineers rank these using the fitting resistance equivalent to PREN. This is what you call fitting resistance equivalent. Percentage chromium plus 3.3 times of molybdenum percentage and tungsten percentage plus 16% nitrogen. If you calculate this one and PREN number comes, let's pick some say 30, 40, 45 like that. We'll see in the following lecture. A PRN more than 40% classifies a material as super duplex, capable of surviving the most punishing marine conditions. The apex, nickel-based superalloys. At the top of the hierarchy are like alloys like Inconel 625 or Historic 276. These are used when the resistance profile requires total immunity to almost all forms of environmental degradation. Use case, high pressure, high temperature, SPST wells, or components handling acid gases, the high H2S, the carbon dioxide that provide. The clay solution, because solid nickel alloys are exorbitantly expensive. Engineers often use mechanical lining or weld overlay. A thin layer of the superalloy is bonded to a carbon steel base, providing the armor of a Ferrari with the frame of a truck. Try to do an analogy like this. A thin layer of the superalloy is bonded to a carbon steel base, providing the armor of a Ferrari with the frame of a truck. I hope you understand this very better now. Let us say comparison, the cost performance. In carbon steel, if you can cost multiplies 1, for example, then key threads are there none. Needs help. It needs help. Common applications are onshore truck lines. 13 chromium stainless steel, it is 3 to 5 times costlier than carbon steel. Whereas its key thread are carbon dioxide, sweet gas. And the main application is the downward tubing. Duplex stainless steel is 8 to 12 times costlier than carbon steel. It is thread is chloride and high stress, which will not resist much more. And common application is the subsea foil line. But nickel alloys, the super, 20 to 50 times costlier than carbon steel. Total cost, corrosion shower, wellhead walls, and XMAS. We'll see LCC and ROI on this one in the forthcoming lecture. We'll understand ROI and LCC in detail. Summary of the hierarchy. Materials selection is a journey from passive defense, that is coatings, to active metallurgy, that is alloying. As the environment moves from sweat to shower and from cool to HIPT, the hierarchy force finds from this one to industry to nickel-based chemistry. Corrosion resistant alloy, CRS. When the fluid is too aggressive, high partial carbon dioxide H2S provides for carbon steel, we move to CRS. These alloys rely on a thin passive chromium oxide layer to stop corrosion. This is just I try to give you a trivial form. Materials stainless steel, Australian stainless steel, duplex, and super duplex. But typical composite I try to show you. Key characteristics are like this: high strain, ductile, austere, superior pitting resistance of the super duplex. The common application where so well head to aggressive subsea production where super duplex is used. Please have a look to this particular table. I will pause for a minute. Let us go ahead. High performance nickel alloys and titanium. For the most extreme SPST, high pressure, high temperature, deep water, or deep gas wells. Here I am talking to Inconel 625 and alloy 825. This provides immunity to almost all forms of localized corrosion and cracking. They are used for the most critical downhole completion components where failure would be catastrophic and impossible to repair. Titanium alloys, exceptional strength to weight ratio. They are very much known for that strength to weight ratio of titanium. and immunity to corrosion stress cracking, used increasingly in offshore riser systems and subsea components to reduce structural weight. Let us see the gold standard of compliance as per the NAS and MPP standards. You cannot discuss metallurgy in ONG without the NAS MR0175 ISO 1515 standard. The intent is what? This standard does not dictate how to build a pipe. It dictates what is safe to use in the presence of H2S. I think this intent is clear. What is the mechanism? It defines limits from the hardness, usually measured in HRC Rockwell C of the metal. If a steel is too hard, it is susceptible to hydrogen embrittlement, we know very well. Engineers must ensure every weld, heat and on, and base metal component complies with the hardness limits specified for the operating environment. It's very important mechanism to be known to meet with this intent. Now let us say holistic mitigation strategy. Metallurgy is only one part of the equation. A mature corrosion management program uses a multi-layer defense. So, my dear participant, forgive me, I'm not dealing only on the metallurgy now. Because if I talk of metallurgy, equation never be over. I must have support from other corrosion management layers for the defense. Let us go in detail to make a holistic image. Chemical inhibition, continuous injection of film-forming amines for carbon steel pipelines. These chemicals absorb, is not absorb, these chemicals absorb onto the metal surface, creating a hydrophobic barrier that prevents the corrosive water phase from touching the steel. Second comes cathodic protection, essential for external pipeline protection. It turns the steel structure into a cathode, that means preventing oxidation by using sacrificial anode like zinc and aluminum or impressed current ICCP. Water treatment, removing oxygen, the primary accelerator of corrosion via vacuum deaerator for chemical oxygen scavengers before water is pumped into injection valves. The 3 points are to be kept to understand the holistic mitigation strategy. Summary strategy, low corrosivity, carbon steel inhibitor, moderate corrosivity, 13 chromium or 22 chromium duplex stainless steel, but high in extreme corrosivity, nickel-based alloys, for example, alloy 2535, 625, or titanium. Designing for the oil and gas industry requires balancing the total cost of ownership, capital expenditure, expensive alloys, versus operating expenditure of corrosion inhibitors inspection against the risk of failure. I would like to repeat the same paragraph, keep in your mind. Okay, designing for the oil and gas industry requires balancing the total cost of ownership against the risk of failure. I hope you are grasping this very well. I hope I'm not getting very, very fast. I want your feedback. Should I slow down or is it okay? Any feedback from the audience? Am I going very fast? Anyway, if it's silence there, I believe it is fine. Material selection for high pressure, high temperature subsea environments. In high pressure, high temperature subsea environments, the corrosion landscape shifts from standard kinetics to a regime dominated by aggressive synergisms. When temperature exceeds 150 degrees centigrade and pressure rises significantly, traditional material boundaries collapse, requiring a transition from standard stainless steel to advanced nickel-based superalloys. Metallurgy in HPHT subsea environments. The core challenge in SPHT is that high thermal energy accelerates cathodic and anodic reaction rates. While high pressure increases the solubility of gases like carbon dioxide and hydrogen sulfide, directly impacting the partial pressure and the resulting corrosivity. Now, let us see the synergy of failure mechanisms. At temperature more than 120 degrees centigrade, common alloys like 30 chrome or 22 chrome to duplex face a threshold where the passive chromium oxide layer becomes prone to breakdown in the presence of chlorides. Here we let us see He and SCC. In sour SPST environments, the kinetics of hydrogen evolution and diffusion into the metal lattice increase exponentially. The temperature sensitivity of CRS, 13 chromium super 13 chromium, often limited to lower temperature due to the risk of sulfide stress taking and chloride-induced cracking. First, let us say 22 chromium to 25 chromium duplex is prone to phase instability. That means formation of brittle sigma phases if not strictly controlled during the welding and heat treatment, which exacerbate corrosion in SPST services. If you talk about nickel-based alloys, say 635 and C718 and 2535, these are the gold standard for SPST. They maintain a stable passive film even at 200 degrees centigrade plus and provide higher resistance to stress causing cracking due to their face-centered cubic lattice structures, which inhibits hydrogen diffusion compared to body-centered cubic BC structure. Now, let us select the protocol. When specifying materials for HPST, the focus must shift to pitting resistance equal number, that means PREN, and the critical pitting temperature CPT. For example, subsequent conditions, one must calculate the alloy resistance based on the specific chloride concentration and partial pressure of sour gases. I am again referring back that PREN equation. High performance alloys for SPST typically requires a PREN more than 40 to ensure stability in deep water brine. Let us see the chemistry of corrosion inhibitor selection. Corrosion inhibitors in the oil field are essentially surfactants that modify the metal liquid phase. Selecting the correct chloride for an SPST environment is a balancing act between thermal stability and the ability to form a persistent hydrophobic barrier. Do not allow water to touch to the substrate. The inhibitor mechanism, let us touch upon this one. Chemisoption versus physiotherapist. The efficacy of an inhibitor molecule is determined by its molecular architecture. The polar head group, this moiety is typically an amine, pyridine, or a phosphonate group, anchors the molecule to the metal surface. The chemisoption provides a stronger, more durable bond by sharing electrons between the head group and the metal debug, which this is essential for SPST environments where thermal energy would otherwise strip the inhibitor from the surface. So it will make the substance helpless. The hydrophobic tail, a hydrocarbon chain, usually C12 to C18, that extends into the fluid phase. And this creates a hydrophobic wall, preventing the corrosive aqueous phase to H2O, CO2 chloride from reaching the metal surface. Now, let us see the critical selection criteria. When formulating or selecting inhibitors for SPST, three factors take precedence. Thermal degradation. Many long chain amines or imidazolines degrade at high temperatures, breaking the bond between the head and the tail. Formulators must utilize thermal stable heterocyclic structures or specialized synergistic blends that maintain integrity above 150 degrees centigrade. There is thermal degradation. Second comes partitioning the coefficient. An inhibitor must partition preferentially into the oil phase if oil soluble or water phase if water soluble, depending on the production flow. In high water cut wells, water soluble, so full forming amines are required. And last is the immersion tendency. One must evaluate the oil water separation capability. An effective inhibitor must not create tight emulsions, that means stable reg layers in separators, which would otherwise cause massive downstream processing issues. So these are the critical area in the selection. So I have given the heading as a critical selection criteria. Thermal degradation, partitioning coefficient, and emulsion tendency. I hope you will appreciate this matter. Optimization for deep water. For long distance subsea type beds, the challenge in fill persistence. The inhibitor is often injected at the wellhead and must remain active over kilometers of flow line. It's a really big challenge. I would love to repeat it again. For long distance subsea tie backs, the challenge is fill persistence. The inhibitor is often injected in the wellhead and must remain active over kilometers of flow line. We look for best treatment capabilities, where the inhibitor can form tenacious, durable film that survives long after the chemical injection has ceased or fluctuates. It's a really big challenge, sir. It's a, it's a best treatment that I'm talking about. Strategic corrosion management, integrating metallurgy, life cycle cost, and safety. To optimize the asset performance in SPST environments, one must translate mere material selection and adopt a holistic life cycle costing and inherently safer design framework. ISD is a really very interesting study. If it is interested, definitely I can give an independent talk on inherently safer design and life cycle costing. Much more people, maybe for 1.5 hours or so. If it is required, so I'll be available to you. The following synthesis aligns metallurgical performance with economic and safety realities, specifically tailored for capital projects within the Indian industrial landscape. The economic link, metallurgy, LCC, and ROI. In the Indian market, projects stakeholders often prioritize initial capex. However, for SPST assets, the corrosion warrior approach demonstrates that investing in higher grade metallurgy, CRS, often results in superior net present value, NPV, and return on investment, ROI, when OPEX, that means OPEX box, that means operation expenditure, chemical injection, monitoring, and inspection, is factored in over 15 plus years. I'm going to the comparison framework for the LCC. Just have a look. Carbon steel plus chloride, initial capex is Indian rupees, base 1 times. OPEX, high dosing metals. Life cycle risk, moderate. Recommended uses, low corrosivity and easy access. Duplex stainless is moderate, 1.8 times. Then the OPEX is low, minimum dosing. Life cycle risk, low. A standard offshore and subsea. But nickel base, king, diamond, gold, it is high. You have to pay for 3.5 times more than the carbon steel. OPEX, negligible. Life cycle case is very low, high integrity. I recommend using SPFT, sour service, and critical. So it has got the life cycle cost is minimum per case. Safety integration, inherently safer design. In corrosion management, ISD dictates that we eliminate the hazard at the design stage rather than relying on active control systems like chemical inhibitors, which can fail. Metallurgy is a safety barrier. Selecting a CRA for the SPST environment acts as a permanent passive safety barrier. It eliminates the human factor, the risk of chemical pump failure, inhibitor shortage, or improper dosing concentration, which are common failure points in our Indian industrial operations. With a really little of sorrow, I am telling you, with my C4 set of experiences where the inhibitor dosage or inhibitor shortage had a big problem in some of the industries and where human factor had entered in. Now, I will not dwell on the human factor. We being human, we know what are our negative points in our mind. Corrosion related containment loss. Under the principle of ISD, We minimize the frequency of inspection and the complexity of the corrosion monitoring infrastructure by using materials that resist cracking by design. Safety benefit reduction in loss of primary containment LOPC incidents. Regulatory environment ensures strict adherence to NAS MR 0175 to ISO 15156, providing a defensible engineering position in safety audits. Let us see the tangible benefits and ROI drivers. When presenting these strategies to management, focus on the following tangible activities if you want to get through. If you want the green signal from the management, these are the matter of internal matter to discuss by the engineers before they reach to the board. Reduce unplanned shutdowns by using CRA in critical sections like heat exchangers, subsea and manifolds. The mean time between failure is very good. Known word for MTBF is a buzzword now for the maintenance engineers, increases significantly. Benefit: avoiding just one unscheduled shutdown in an Indian refinery or chemical plant can save tens of crores in lost production. Lower insurance premium. Asset integrity management, which is my buzzword now. Since last few years, I'm working only with the asset integrity management programs that demonstrate the use of high-grade, risk-adjusted materials often qualify for better insurance risk profile. So you have to pay little less premium in this case. So in long run, this driver will be helpful to you to reach to the board of directors to get the sanction. Decrease inspection frequency. High integrity alloys require less frequent non-destructive testing and intelligent pinging, reducing OPEX related to specialized inspection, labor, and logistics. Environmental compliance. Minimizing chemical inhibitor usage reduces the toxic load in the produced water stream, lowering the capital and operating costs of the effluent treatment plant. I am going to have, we have line, I am going to throw one webinar on effluent treatment plant. Their corrosion plays an important role. I think I will be making a note that when I am going to have it on the air. This is the case. We have to wait to work. To implement this, apply the following hierarchy of decision making for any new project. Define the fact envelope. Establish the partial carbon dioxide, partial hydrogen sulfide pressure, temperature, and chloride concentration accuracy. Evaluate material against LCC, life cycle cost. Conduct a life cycle cost analysis using cost for material procurement versus projected chemical injection cost over 20 years. Apply passive protection. Prioritize higher metallurgy to remove the reliance on active systems like inhibitors, cathodic protection, like that, wherever the environmental severity justifies the capex. Verifications. Implement a robust NDT plan to validate that the selected metallurgy is performing according to the predicted corrosion rates. That means corrosion allowance management. I hope this matter is quite fine in your mind. Define the fact envelope, evaluate material against LCC, apply passive protection, and verification of all these things against the corrosion allowance. By shifting the culture from repair and replace reactive to design for integrity, that is proactive, you transform the corrosion function from a cost center into a value preservation energy strategy. Comprehensive corrosion management. What is that? An integrated framework of HPST oil and gas assets. In the modern oil and gas industry, corrosion management is not a series of isolated tasks. It is a unified discipline that links metallurgy, chemistry, economics, and safety. With permission from my organizers, I added this one. Why? Okay, that is the modern oil and gas industry. Corrosion management is not a series of isolated tasks. It is a unified discipline that links metallurgy, chemistry, economics, and safety. To successfully manage high pressure, high temperature subsea environments, one must apply a holistic strategy where every decision from materials grade to chemical dosing is validated by life cycle costing and inherently safer design principles. My dear participants, you would like to read particular this snap. You digest it. This is the way we are going to rolling around. To successfully manage high pressure, high temperature subsea environments, one must apply a holistic strategy where every decision from material grade to chemical dosing is validated by LCC and ISD principles, which I am practicing since last a few years. And that's why I'm getting sometimes a clap from the management. Yes, this is the way we should look into. Defining the threat envelope, the foundation. Before any engineering decision is made, we must define the threat envelope. What is that? In SPST environments, the synergism of high thermal energy and pressure increases the solubility of gas like CO2 and H2S, directly accelerating corrosive reaction rates. The combination of more than 150 degrees centigrade temperatures and high partial pressures of CO2 and H2S renders traditional carbon steels inadequate as they become susceptible to sulfide stress cracking and hydrogen-induced cracking. The metallurgy response. Our first line of defense is material selection. For HPHT, we move away from standard alloys to high-performance corrosion alloys with a pitting resistance equivalent number of more than 40. In this, what will you see the hierarchy? 13 chromium to super 13 chromium. It is suitable for a moderate temperature limited by ACC risk. You have to be careful, the ACC risk is definitely prevalent over there. Duplex, high strength and chloride resistance, but requires strict control of the microstructure to avoid brittle sigma phase formation. So welding plays very important role. Welding plays very important role. I have seen it 2257, 2507, super duper industrial. I've seen in some of the industries where as casually the welder, without getting any advice given by the supplier, they hit the surface. And because they feel the moisture should be removed, so the torch they hit the surface and they go welding. And they make this material as costly as gold within a few months in the structure. So this is very important. High strength and chloride resistance, but requires strict control of the microstructure to avoid brittle sigma phase formation. So nickel based alloys, alloy 625, 718, 2535. The gold standard for extreme HPHT. These provide immunity. This is immunity to almost all localized corrosion by maintaining a stable passive film in the most aggressive brine chemistries. The integrated mitigation strategy, metallurgy and chemistry. Metallurgy, passive protection, and chemical inhibitors, active protection must function in tandem. It must function in tandem, metallurgy and chemical inhibitors. A common error is viewing this as separate options. They are, in fact, a single integrated system. Passive protection, that is metallurgy, utilizing CRA components provides a permanent low maintenance barriers. This directly satisfies inherent safer design principles as it reduces reliance on active chemical injection systems that are prone to mechanical failure. Active products like inhibitor chemistry. When carbon steel is used to economic feasibility, we deploy film forming inhibitors. In STFT service, the chemistry must be rigorous. Thermal stability, what we have seen in the previous slides, the inhibitor must resist degradation at, it is wrong degree, 150 degrees centigrade, zero by mistake. I'm very sorry for this one. It's not 1500 degrees centigrade, it is 150 degrees centigrade. I'm sorry for this my mistake. We prioritize heterocyclic structures that maintain a strong chemi-shop bond with the metal surface. Partitioning. The inhibitor is selected to partition effectively into the water phase, forming a hydrophobic barrier that prevents the corrosive brine from reaching the steel. Economic alignment, LCC, ROI, and market realities. In the industrial context, procurement decisions are often constrained by initial capex. However, to maximize the return on assets and minimize operational risk, procurement strategy must shift to life cycle costing. The LCC calculator is a decision-making engine. CapEx versus OpEx, the trade-off. Investing in a CRA, for example, nickel alloys, result in a higher initial Indian rupees expenditure, but dramatically reduces the OpEx associated with the chemical dosing, monitoring, and frequent inspection. For a typical facility, avoiding one unscheduled shutdown, often valued in tens of crores of rupees, is the primary driver for high-grade material selection. So let us say risk cost mitigation. High-grade alloys require less frequent NDT and intelligent pigging. Enhanced material integrity lowers insurance risk profiles and reduce the environmental liability associated with leak-prone pipelines. So we are now ending up with my presentation. Let us take away to resonate with you. What are the pillars of integrity? A final summary. In the oil and gas industry, we don't just fight chemistry, we engineer resilience. What I say? We engineer resilience. The battle against corrosion is won through a strategic hierarchy of defenses that ensures the longevity of our assets and the safety of our environments. The first line of defense is material selection. Metallurgy is our foundational side. By selecting the right alloys, whether it's carbon steel for standard environments or corrosion resistant alloys for sour service, we address the threat before the first drop of oil flows. First line of defense. Keep in mind, sir. Second is the active guard, environmental modifications. When the environment is inherently hostile, we change the rules of engagement. Through inhibitors and water treatment, we neutralize corrosive agents like hydrogen sulfide, carbon dioxide, and fluorides, creating a chemical barrier that protects the metal from within. Third is the external shield, surface protection. We leave nothing to chance. That is the reason. Coatings and hydrogen protection provide the final layer of security, acting as a physical and electrochemical barrier against the relentless elements of the earth and sea. So what is the bottom line? Corrosion management is not a cost center, it is an integrity strategy. I have defined like this, sir. But you permit me. Corrosion management is not a cost center. People do not go for corrosion management, but it is an integrity strategy. By mastering the intersection of metallurgy and environmental science, we transform critical threat into a managed variable, ensuring that our infrastructure remains safe, sustainable, and profitable for decades to come. So, what are the key takeaway? We don't just build for today, we select, treat, and protect for the lifetime of the asset. So, select the right metallurgy for the specific chemistry, modify the environment to reduce the corrosive drive, and protect the surface to ensure zero fail performance. So, thank you for listening, sir. Yes, madam, anything from your end?
Yes, sir. I request for All delegates to unmute yourselves and ask questions if you have. You may also type your questions in the chat box.
Can I start with?
Yes, sir.
No.
Yes.
Yeah, very good afternoon. Nice to
Good
hear
afternoon.
you after a long time.
Yes, sir. It's
So
my privilege to be with you, sir.
yeah,
I'm overwhelmed. Really,
yeah.
you remembered me to
Mhm.
address the
Thank,
audience, sir.
thank you very much. Taking up very important session for our engineers because we keep on facing a lot of problem while welding, while metallurgy, while selection, while casting. So
Yes, sir.
when they do the inspection, they come across many. And first thing I would like to salute and thanks our
So so I have.
Corrosion Wizard.
Oh no, sir.
Yeah.
No, please.
He is
Don't miss it.
well known corrosion scientist, and fortunately, we have been associated last 5 decades. It's a
Yes, sir.
long time we have been associated, and there has been a lot of achievement by Dr. Thanki sir. He is lifetime achievement award from NIS for his services to the nation for corrosion. He has presented many papers on metallurgy, corrosion, laboratory related to metallurgy, and he is also instrumental and motivator to attract corrosion engineers and make them aware about corrosion and because corrosion field no engineers want to go into it, but one has to motivate. It's a very complex, I should say, because it is very important. And today, world is very much concerned about the climate change. As Dr. Thanki has also told, environment plays very important role, whether external environment or internal environment. So that plays and selection right, mitigating right corrosion mitigation is most important. Second thing also, world is worried about not only climate change, life cycle sustainability. Because whatever we plan, we do, we construct, we spend our infrastructure, assets, so it has to last for long. Its life cycle. Even ISO is also talking both the system. One is the climate change, one is the life cycle, which Dr. Thanki has connected very well with the metallurgy and corrosion. Thank you very much, sir. So I don't want to
Thank you,
take
sir.
much time.
No, it's
So
fine,
let
sir.
other
I
people
took
to.
little advantage, sir. I wanted to say the holistic view to this methodological aspect because
Yeah,
single methodology will not help us, sir.
yeah. Because you had
Yes,
touched upon all the aspects of corrosion and corrosion management and metallurgy. That was important to connect each other. So
yes,
our
sir.
engineers will be overwhelmed and they will learn from this attending this seminar. Thank you, sir.
I will
Thank
looking
you.
forward to another opportunity, sir. Another opportunity to talk to you. Please give me
Most,
some platform. Huh?
yeah. Yeah. Back to you, Pranali.
So, Tanki Sab, one more. Uh, First of all, it is amazing listening to you, sir. As always, it's for people over here who don't know you. You are legendary in this field, and it's so humble with so much knowledge. It's an honor to have you on this platform and listening to you, sir. Sir, I would like to know some insight from you. Why does the industry typically take design stage so lightly? Because everybody thinks that, whatever you will do, whatever workmanship you will do, you will just put the secondary protection in place and try and do cathodic protection through ICCP or sacrificial, and your assets will get protected for a lifetime, where the
Mhm.
major concentration or the major effort should be in good designing, good metallurgy, good material selection, because that's the heart of the system. But unfortunately, we see the design, they are always very lax, material selections, they are lax, or they just use a very standard set of operations. What is your insight of so many years, 6 decades you put into the industry? Are you seeing any change in the way it is being done today?
First thing which comes to my mind is a very good question, really. It always focuses me all the time. But human factor plays very important role. Human factor in the sense they would like to start a plant early as possible. They will not wait for for example, surface preparation of the structural steel. It is a very dirty job. They will say, yes, complete the surface and go on painting. Now, as we all know, the surface preparation takes more than 70% of the life of the coating. Best paint will fail within a very short time. And good surface preparation give you a very cheap paint to longer time because there will not be any bonding or anchoring of the coating on the surface. That is first thing, sir. Second thing, because of I have seen in the Gujarat, particularly the coastal line, which is more than say 2,000, 3,000 kilometers from right from the Kutch to the Bharuch Surat. I have seen many industries which are moving knowingly to the coastal side, but they forget that they are knowingly entering the highly corrosive area. So the design criteria changes when you are moving to the coastal side, but they behave as if it is in the Nagpur or Delhi or somewhere else. So they do not go in detail, and that is first thing, sir. Second thing I have seen in my life is the design stage, which is also my empathy many times when I was with GSFC also. That when they are designing anything, particularly the corrosion or materials man will not be the team member. They take it for granted. Second thing, they would like to hurry up to complete the project. They cut the corners in many things. If 304 stainless steel can go well, we'll not think of 316. But because cost factor will be very big thing, and he will be getting the pat from the management, and project man will be certified. Whereas the people who are going to practice it or the fabricated the whole structure, they will face a lot of problem. So human factor plays very important role, sir. I hope you know that very well. I just made it a little more clear to you.
Absolutely, sir. Well said, sir. Thank you so much for all the insight. Thank you for taking this session.
Thank you.
Anandji, would you like to say something? Anand, sir,
Yeah. So, Samiti, I just want to add to some answers to your question.
please, sir. Please go ahead.
Yeah. I just want to add to some responses to your question. Since let me tell to Mr. Dr. Tanki also that I have done my master's in applied chemistry from Faculty of Technology and Engineering, MS University of Baroda. And I believe Dr. Tanki is from the same place. And I'm currently located in the Republic of Azerbaijan in the oil and gas industry in the offshore activity. So this subject was very well interested that.
Hello. Hello.
I think he's joining us from far, so we'll just give him a minute.
Yes. It's good that they're joining with us, really.
Yeah.
How many participants? By the way, how many participants are there today?
We had about 70. Now we are left with about 57.
70 to start with, right?
Yes,
Okay. Good.
Yes. Anand sir, you would like to say something?
Sir, first of all, I thanks, and it was a wonderful session, sir. And I have been into corrosion session many times, but that detail which you have covered, it is extremely good, and it is always being a question to us during our assessment and during our visits. One thing, sir, I would like to know. Is there any requirement which relate to our precision equipments like gauges and other things? Because that is again a area which is not at all seen. It is only calibrated, but not seen somewhere, like not comes into the process anywhere.
I think it is the management problem rather than the utility of the gadgets. No, people are not aware of its utility. And that is the reason only. I believe so.
Okay.
Yes, Anandji, we have Menon Saab back. So Menon Saab, we can hear you now. Please go ahead. You can complete.
Yeah, I said there's some network glitch was there, so I believe that's what I got disconnected. See, I just know adding that offshore environment nowadays, this design criteria is taking a forefront because looking to the challenges, especially on the HSE side, safety and environment side, there is well advanced plannings are taking place as per the well criteria, the designs, especially on the material selections. As one of the slides was touching on the high pressure, high temperature wells. So where the material selection is playing a very critical role. Some
Yes, yes,
areas of the offshore is hydrogen sulfide infected wells, where
yes,
the
sir.
corrosion is highly, plays a role to which degrade.
Yes, sir.
And because in the alloy steels, the phosphorus and sulfur, these are the two
Dylan.
elements which significantly degrade the corrosion.
Yeah.
So, so there are various alloy steels are available according to the carbon content. Like you might be heard about 4140, 4145, 4130 grades.
Yes, yes, yes,
And
yes.
for the corrosion resistance, the 13 CR LIT material, 13 Super 13 chrome. Then nowadays, 25 chrome is getting replaced by Inconel material,
Uh-huh.
718 and Inconel 925 material. So
Yeah.
which gives an advantage to the high sensitive deep wells in the oil and gas industry.
Mm-hmm.
So
Yes.
yeah, today's insight from you is is a very meaningful and value addition to people like me, and
Mhm.
looking forward to hear such subjects in the coming days. Thank
I
you
feel
once
happy.
again, Mr. Tanki and Dr. Sundar Katari and Sumitji, because these are the subjects. No, this is the need of the hour for the industry, especially to the
Yeah.
oil and gas industry.
Yes, 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 yes. Yes, sir. Thank
And
you. Thank you,
I,
Mr.
I
Menon.
would like to just add, it is only because of people who like Dr. Thanki, who are so knowledgeable and yet so humble that they come to these platforms and want to share the knowledge so that all of us can gain. And it's for listeners who are here who, make it meaningful for the presenter to actually come and share his knowledge. So such sessions which are, created and crafted by Kataria sir, these are very important. But unfortunately, not too many people partake in this, and I am honored and thankful to Thanki Sahab and each one
Oh,
present here,
please, please.
for who have removed time to gain knowledge, because these are all value additions to every individual. Every individual sitting here, I'm sure, walked away with a lot of knowledge that Thanki ji openly shared with everybody. These sessions, believe me, are so valuable that if Thanki ji has to actually roll out so much information and people would pay out of their pockets to actually attend these sessions, and here he's done it out of such a noble initiative. Thank you so much, Thanki Sahab. Really honored
Thank
to
you.
hear you. If there are
Thank
any
you.
more questions that anyone has, I would love that you please clear your doubts, because he's the master of metallurgy. So you rarely get opportunities to, hear from the
If,
expert.
if at the moment, if the question doesn't strike in your mind, then
Yes.
contact me on my email. I will
Lovely.
be
Sir, if you can
answer.
share your email ID on the chat box, or I will ask Pranali to send it to everybody.
No, probably knows this my number.
Yes. Pranali, please share sir's email ID on the chat box. So if you are remembering any question later on when you're doing something and you get stuck with metallurgy, Thanki Saab is the go-to man in the industry. He needs zero introduction. For people who are in the corrosion fraternity, he's like one of the Brahmas of the field of corrosion. So
Please,
thank you
please,
so
sir.
much, Thanki Saab.
Yeah.
Thank you. Thank you a lot. Thank you a
Yes,
lot. Thank you.
Pranali, if there are any questions, we'll take some questions. Last question. Anyone? Kadaria sir wants to say something.
Yes,
Please go ahead.
Kataria sir wants.
Dr. Thanki has told that hydrogen is also one of the minerals. And we also
Oh,
find in welding and doing
ah,
metallurgy, hydrogen
yes.
is very dirty room. And I just wanted to, sorry to use the dirty, but I want to know the space technology and how the hydrogen, liquid hydrogen used as a fuel. What is the metallurgy they use for the tanks so that it prevents corrosion and abnormal failure?
You know, sir, that the stainless steel is supposed to be the quite a strong material to withstand against the hydrogen in a nascent form to penetrate through. So they go metallurgy with the higher metallurgy with the higher chromium nickel material. And that is the only way one can go to reduce the hydrogen effect on the material when it's passing in the uh, various places where it is liquid hydrogen to be handled. So the more of this thing is stainless steel which is on because of its you can say metallurgically it must have the minimum porosity, and that is the I can say the level of hydrogen is a nascent form should not percolate through. So the stainless steel, high grade stainless steel is the only way to go, sir.
Okay. Thank you, sir. Thank you.
Thank you, sir. Thank you. Okay, see you then again sometime.
Everyone, I have shared Dr. Thanki's email ID in the chat box. If you have any questions, you can consult with him.
Right. And Pranali, over to you for the closing.
Yes. One more time, I'm asking everyone, if you have any questions, please ask.
I think no more questions, Pranali. You can
Yes,
proceed with the closing.
I see there's no more questions anymore. So we are going ahead. Before that, on behalf of entire ICS and all the participants present today, I would like to extend a heartfelt thanks to Dr. Thanki sir for your insightful presentation on metals and metallurgy for oil and gas industry. To control and mitigate corrosion, your valuable knowledge and clear explanation have greatly enriched today's Sadhguru Sangh session. We truly appreciate your time, effort, and contribution. We truly honored to have you today, sir. We look forward more learning from you in the future. Thanks a lot, sir.
Thank you, Pranali. Thank you. Thank you, Pranali. Thank you.
Yes, Pranali, you can share your screen.
Thanki sir, can you please stop your screen sharing?
Yes, sir. Yeah. I will do so.
Yeah. So is my screen visible?
Yes, Pranali, we can see your screen, but it's on display. Please open that presentation.
It's visible, no, sir?
No, not on my screen. We can take confirmation from someone else.
One second.
Yes, we see your screen now. Please go ahead.
So ICS is placed to provide you all its research and development, integrated management system, QMS, EMS, and OHSMS, excellence in education management, ISO made easy in Gujarati, Marathi, Telugu, and Hindi. Our recent publications, first one is Urja, Thermal, Oil and Gas Nuclear, and second one is Jung Se Jung Tak, Fight with Rust, Corrosion Causes and its Mitigation. For reading any of the above books, please contact Ms. Sushma Kindlekar. Feedback form, please register on www.sadgunsang.org and go in your login and give us feedback. I would also like to thank all our participants for their valuable time and active participations. We hope you found the session informative and useful. Have a nice day.